So drug abuse has long been a major problem in American society, and new challenges are being brought by the rise of vaping, especially among teenagers, in the current opioid crisis. So we attempted to model the growth of vaping usage. We also look at how to predict the probability of drug use of several different drugs based on various demographic factors, and finally worked on quantifying the impact of some of these drugs on American society as a whole. So first we were looking at nicotine specifically, and specifically with new nicotine sources such as vaping. So we developed a mathematical model for the spread of nicotine use due to vaping over the next 10 years. And then we took that model and compared it to how the growth of traditional cigarettes will compare with that of vaping products. So first we did some background research, and we found that nearly 90% of adult smokers begin before the age of 18. And that's data from the U.S. Department of Health and Human Services. We also found that when you look at among smokers below the age of 18, the rates are very low until high school age students. So people who are beginning before age 18 are usually beginning in high school. And these are the people who will continue to be smokers into adulthood. The vast majority of adult smokers are accounted for people beginning in high school. So we approximated that the growth or increase of nicotine use from a given source in a given year should be approximately proportional to the high school use in that year. So then we looked at data, and for all of these we used data from the National Youth Tobacco Service and focused on use within the past 30 days. That's how we define drug use in all parts of our model. And so we looked at this data and we found quite a strong exponential fit. But if you think about it, you can't extrapolate an exponential curve indefinitely. We look, for example, in the year 2024, we would be predicting that almost 200% of high schoolers would be using e-cigarette products. That doesn't make any sense realistically. So an exponential model isn't quite right. But if we think about these vaping products, especially ones using kind of USB style designs, they're relatively new to the market, and so this kind of exponential explosive growth can be explained by that. But in the long run, we expect the market to stabilize as these become more normal. So we expect a somewhat logistic model. And also, we are projecting for the next 10 years. We expect that beyond that, there might be policy changes that will change that trend and maybe bring these numbers down. But looking in the relative short term, we project this logistic model. And so we solved the differential equation for the logistic model for the P of T, the predicted proportion of teenagers who will be vaping in a given year, T years after 2011, and found that the best fit approximately was at 32.5% at our leveling off point. So we also looked at traditional cigarettes, and we found a very strong linear pattern with an R-squared value of over 97%. However, again, we can't extrapolate linearly infinitely. We'd go below 0%. So we assumed the lower bound of 3% in our linear model because it's going to have to level off at some point, and anything within the range of about 1 to 5% won't really have much variability in the calculations at the end of our model. So then moving on, these shows the main parts of our model. We've got P of T, the predicted proportion of teenagers or high schoolers who will be vaping in a given year, T hat, the predicted proportion who will be using traditional cigarettes. And then if we take the sum of those two, since that should be proportional to the growth in nicotine use in a year, that would be kind of the magnitude of nicotine use growth in a given year. And then we take the fraction of that that is due to vaping to find how much of that's accounted for by vaping. So let's just look at kind of our final data. So first, graphically, we show the relative magnitude of nicotine use by year. We see this will be a growing problem. It's already starting to grow due to vaping products. And we expect it to level off in the mid-2020s. But remember, this is looking at growth. So if the growth levels are higher, that means it's becoming an increasing problem that resource should be focused on. And finally, we look at the percent in our model that can be accounted for by the growth in vaping, and we expect that to go over 90% by the year 2021. So we think that resources should be focused towards vaping awareness and prevention. And I'll pass it on to Angela to talk about part 2.
Thank you, Joey. In part 2, we were tasked to create a model to predict the probability that an individual uses marijuana, alcohol, unprescribed opioids, or nicotine based on their demographics. We then applied our model to a sample of 300 high school seniors with varying demographics to determine usage of the 4 drugs. To create our model, we first determined the 4 most influential factors. Based on the detailed reportings from the National Health Institute on gender, age, race, and poverty level, we decided to use these in our model. So our model was a weighted multiplier system that determined how much more or less likely a person would be to use a drug. So using this table, we created multipliers, and by using multipliers, we were able to maintain the independence of the influence of each factor. So this first ensures that the usage ratio between subgroups in a given demographic is independent of other factors, and it also maintains the sample proportion usage of a drug. So to calculate a multiplier, we first multiply the proportion of the population in the subgroup with the proportion of subgroup that uses the drug. We repeat this for each subgroup to arrive at a sum of the products. And to find a specific multiplier, we divide the proportion of the subgroup who uses the drug by the sum. So to find the multiplier for an individual using marijuana while under the age of 18, we would take the usage statistic of 0.065 and divide that by the sum, which is 0.08842, and arrive at a multiplier of 0.735. And so figure 2.2 has our multipliers for the various drugs and demographics and subgroups, and figure 2.3 has the national substance use. So an example case of calculating the actual probability is if we have a 23-year-old African American female at a 100 to 199% poverty level. To predict the probability she consumes nicotine, we would first multiply the 4 multipliers for her demographics to arrive at an index of 1.4926, and we would then multiply that by the national use statistic of 15.4%, and we arrive at a 22.9% chance that she will use nicotine. Now Matthew will go over the applications of our model.
Thank you, Angela. So now that we have each of the multipliers, we wanted to find the index values for each of them. So since there are 288 unique combinations of these multipliers to calculate the index values, we decided that instead of doing it by hand with the calculator, we'd use code instead, just to save a lot of time. So some of the outputs are here. This is not all of the output because I couldn't fit it on the slide, but it is just a sample. Right. Next, we were tasked with predicting the drug use for a class of 300 seniors. So one key assumption that we made is that this class is demographically representative of the United States in every way except for age. So we assumed that a senior is in the 18 through 25-year-old age group because an 18-year-old senior will have just as much access to a drug as a 17-year-old senior due to social circles and social factors. So for example, since 22% or 22.1% of Americans aged 18 through 25 use marijuana, we multiplied 0.22 by 300, and we calculated that 66 of these seniors would use marijuana. And we repeated that process with each of the drugs. And finally, we decided to validate our model. So the first thing we noticed is that alcohol of the 4 drugs presented is the most sensitive under our multiplier system. And the reason for that is because alcohol is the highest percentage of use at 56.3% of the nation, while opioids have the lowest percentage at 0.3%. So if we take a hypothetical multiplier, or an index value of 1.4, then 56.3 times 1.4 is further away from that mean of 56.3 than 0.3 times 1.4. And we decided that this high sensitivity is justified because of the high access to alcohol. And then we also looked at each drug individually. For example, with marijuana, the lowest multiplier is among the Asian race at 0.40289, and the highest is among 18 through 25-year-olds at 2.499. So when we divide 2.499 by 0.40289, we get a quotient of 6.2. This means that for the marijuana category, no one multiplier will have more than 6.2 times the impact as another. And now Tony will begin our presentation on part 3.
Thank you, Matthew. For part 3, we were tasked with the following. First, to develop a metric to quantify the impact of substance abuse, which considers both financial and non-financial factors. Second, to rank nicotine, marijuana, alcohol, and unprescribed opioids based on their respective impacts. To accomplish this, we decided to use an annual social cost benefit analysis model of drugs in the United States, which compares non-financial and financial factors by assigning monetary values to typically non-monetary ideas. Our model is composed of three major components: the total market value, which accounts for the total economic benefit due to the sales of the drug; the humanitarian cost, which accounts for social costs due to direct deaths and addiction; and finally, the external cost, which is a summation of lost productivity, criminal justice, and social welfare. Over there is a chart detailing the total market value of each drug in the United States in 2017. For the humanitarian costs, we scaled different statistics with the value of statistical life, or VSL, which is essentially the amount someone would pay to extend their life by a certain amount, extrapolated outwards to an entire human life. Additionally, since the average human life expectancy for a U.S. citizen is 78.69 years, we found that the VSL per year is approximately $122,000. Now we have that H, the Humanitarian Index, is equal to lowercase p, which is the number of direct deaths due to a drug, times VSL, plus A, the calculated loss of life. And so the left side of this equation, p times 9.6 times 10 to the 6, is accounting for the social costs due to the direct deaths of the drug. On the right side of our equation, we have calculated loss of life. A is equal to uppercase P, which is the number of people addicted to a drug, times DW, which is a disability weight from 0, which is perfect health, to 1, which is dead. And that accounts for from the Global Burden of Disease study in 2016, that approximates how much of someone's life someone is losing due to being addicted to this drug. And then we multiply by $122,000. Here's a sample calculation for nicotine of both loss of life A and the total humanitarian index H, and our results for all of the drugs. Next will be Joshua Tsai to conclude our presentation on part 3 and to conclude our discussion on drug abuse.
Thank you, Tony Tang. We then move on to analyze the impact of the external costs on the United States economy. We determined that the three most impactful factors of the external costs would be the loss of productivity, cost of social welfare, and the cost of criminal justice. To quantify the total loss of productivity due to increased rates of absenteeism in workers affected by substance use disorders, we use the following equation, where P represents the loss of productivity in dollars per hour, or dollars per year. D2 minus D1 represents the difference in the average amount of days lost per year by workers affected by a drug and not affected by a drug. I is the annual median income for American workers, and N is the number of workers affected by each drug. Using our equation, we generated the following values, which you can see in figure 3.7. To conclude our analysis of the the total external costs, we analyzed the social welfare costs and criminal justice costs, as can be shown in figure 3.8. Note that we also included the cost of drunk driving under the social welfare costs for alcohol, as is considered one of the most influential aspects of the costs of alcoholism. Using the results of our research, we summed the three most influential factors of each drug for the total external costs to get the values shown in figure 3.9. To conclude our part, we define the total annual index, which symbolizes the total societal impact on the United States. We use the following equation, where TI represents the total annual index, M is the total market value, H is the humanitarian costs, and E is the total external costs. Ranking the drugs in terms of increasing impact on the United States society is alcohol, marijuana, unprescribed opiates, and then nicotine. Our results make sense in light of the significance of the humanitarian costs. For example, because nicotine has one of the highest disability rates, it also has the highest rate of addiction in the United States, whereas alcohol has one of the lower disability rates and also the lower rates of addiction in the United States. It makes sense that those two would be the polar opposites of our ranking of each drug. One benefit of our model that you may realize is that we separated the total annual index into three different parts, which allows for people to analyze which statistics that best suits their interest. For example, they can take the total external costs when trying to rank the total impacts of each drug on the United States economy. And here are our summary statements. In part 1, we modeled the growth of vaping and compared it to the uses of cigarettes. In part 2, we found the probability of a person to be addicted to marijuana, unprescribed opiates, nicotine, or alcohol, and applied it to a class of 300 seniors. And in part 3, we found the impacts of financial and non-financial factors of marijuana, unprescribed opiates, nicotine, and alcohol, and then ranked their magnitudes. This concludes our presentation. Thank you for your time.
great job. Congratulations on making it to this stage of the competition. I just had a question from part 3, question 3. So in your analysis, there is VSL, loss of productivity, and criminal and other social costs. Depending on the definition of each of these, there can be some overlap. How did you account for not double counting?
So when we were looking at the accounting for criminal justice and social welfare in comparison to VSL and the value of statistical life, we had VSL represent more of like the internal costs or like the individualistic costs of a person who dies or is affected or addicted to a drug. And thus we did not expect there to be much overlap, as like the social costs due to like social welfare is different than the costs of like an individual and their effects on the people around them.
So in question 2, one of the things that most teams had a difficult time doing was somehow incorporating social influence and peer pressure, things like that. How did you do that in your model, or how did you think about that?
So in our model, I think most social factors we consider to be a part of the age and income level statistics. So for those aged 0 through 17 years old, they're minors, and so perhaps the influence of drugs on their peers using drugs will be distinct from those aged 18 through 25, and that would be inherent in the drug usage statistics that we used in our model.
Okay, so for question 3, we over reading lots of papers saw that students kind of struggled with a way to define robust, or maybe didn't write really a firm definition of what that meant when they were defining their model. So could you tell us a little bit about what you were thinking in terms of your metric being a robust approach to answering Q3?
Could you please define what you mean by the word robust?
Actually, that's what I'm asking you to do.
So, when we were thinking about our model, we really wanted to account for, as I stated before, the individualistic costs and more of the individualistic perspective of a person and their effect on like the community around them, rather than macroeconomic costs of like the entire society as a whole. So one of the first portions of our model that we developed was the humanitarian costs, which is more unique and was based off of like ideas from psychology, where we talked more about how different events stress different people differently, and then we decided to use VSL as a representation of that.
I'd like to ask you some questions about question 1. When you were looking at cigarette use, you decided to use a piecewise linear function for your model, but when you were looking at the rise in the use of vaping, you decided not to go that route. Why did you decide to go one way with the first model but not the other model?
So first I'll talk quickly about with our model with respect to traditional cigarettes. So we saw such a strong linear trend, and we saw no signs that that trend was ending, but obviously it has to at some point once the levels get low enough. And for that aspect, the 3% was not intended to necessarily be a precise estimate because we weren't sure how to create necessarily an exact estimate of when it will level off. However, we figured in that case, it will continue to decrease. All the signs point to it to continue to decrease, but mathematically it can't go below 0, obviously. So in that case, we felt comfortable making that mid-range assumption because since our vaping model would have such higher values in terms of the overall magnitude, whether we got 1%, 3%, 5%, it wouldn't have much of a difference. With our other model, we realized that a logistic model could go for the long term because it's feasible for a logistic model to continue indefinitely. And kind of the idea of a logistic model is that it will continue indefinitely as long as there are no changes. So we assumed, okay, if there are no necessarily major policy changes, this is what we project. And we do recognize that there probably will be some policy changes, but we expect that for the short term or for the next few years or the next 10 years, that trend can realistically continue, and it doesn't have any mathematical impossibility involved.
Sorry. So when you talk about the logistic model going on, what do you mean by that?
So what I mean is, well, let's say that in comparison to an exponential model. If you have an exponential model continuing indefinitely, well, it's going to continue to increase the proportion at an increasing rate. We're going to see projecting that 500% of high schoolers will be using a given product. That isn't possible. When I talk about a logistic model continuing, I'm saying, what does it project 10 years from now? Is that a reasonable value? Is that within the range of, well, obviously 0 to 100%, but also within the range of reason based on what we've observed so far?
Thank you so much. Congratulations again. You did a great job. And I think you're going to head